At its core, collecting data from the internet requires a remarkably simple algorithmic loop. You give a program a starting URL. It fetches that web page, extracts all the hyperlinks found in the HTML, appends those new links to a queue, and repeats the process. In a basic Python script, the loop executes in milliseconds. The graph of discovered URLs expands exponentially. Within minutes, the program rapidly freezes and shatters. This naive crawler fails across multiple dimensions. The first failure is local memory exhaustion. Because the web contains trillions of links, appending every discovered URL into a standard RAM-based queue quickly consumes all available system memory, crashing the machine. The second failure occurs over the network. If your queue happens to fill up with thousands of links pointing to a single website, your loop will execute them sequentially. You will send thousands of requests per second to one server, effectively executing a denial-of-service attack. The target server will crash, and your crawler's IP address will be permanently banned. The third failure is thread starvation. Standard domain name resolution, converting a URL into an IP address, is synchronous. If a target server is slow or malicious, your crawler thread waits. If a site creates an infinite loop of auto-generated links, a spider trap, your crawler gets stuck resolving dead-end paths while the rest of the web goes unindexed. Building a crawler is an exercise in surviving the physical limitations of network input and output. To process billions of pages, the architecture must completely decouple the scheduling of what to fetch from the actual execution of the download. The scheduling component of a crawler is called the URL frontier. It faces a strict mathematical conflict. It must prioritize high-value pages, ensuring authoritative sites are crawled frequently, while strictly enforcing politeness, the rule that a crawler must leave a designated time delay between requests to the same host. This diagram shows the Mercator architecture, a queuing pipeline designed specifically to solve this conflict. It splits the scheduling process into two distinct stages: front queues for priority and back queues for politeness. In the upper half, incoming URLs are assigned a numeric priority score. This score is calculated using variables like the parent page's link equity, its PageRank, and its estimated rate of change. High-scoring URLs are routed into high-priority front queues, ensuring the crawler doesn't waste time on stale or irrelevant domains. In the lower half, the system extracts URLs from those front queues and routes them into a series of back queues. The routing logic here is strict. Every individual back queue may only contain URLs belonging to exactly one host domain. To enforce the delay between requests, the system maintains a min-heap data structure. This acts as a countdown timer for each back queue, tracking the exact millisecond that domain is allowed to be contacted again. A worker thread is only handed a URL when the timer for that specific domain reaches 0. Because a web-scale frontier manages billions of URLs, it exceeds the RAM capacity of any single machine. The queues are stored out of core, meaning the bulk of the data is written sequentially to persistent disk storage, while only the small head and tail buffers remain cached in memory. By isolating priority sorting from domain-specific rate limiting, the Mercator structure guarantees that the crawler will never overwhelm a target server, while continuously feeding the highest-value URLs to the worker threads. A single machine is physically constrained by CPU cycles and available network sockets, maxing out at roughly 1 to 200 page fetches per second. Indexing the web requires thousands of worker nodes operating in parallel. Scaling out introduces a distributed coordination problem. If multiple independent crawler nodes happen to pull URLs from their local queues and hit the exact same domain simultaneously, the aggregate traffic will violate the rate limits and trigger an immediate ban from the target server. This diagram shows a consistent hash ring, a structure used to implement host-based partitioning. Instead of every node crawling random URLs, the hash ring maps specific domain names exclusively to designated nodes. This creates domain affinity. When a URL is discovered anywhere in the system, a distributed message broker like Kafka routes it directly to the one specific node assigned to that domain. Because only one machine ever communicates with a given website, the local min-heap timer on that machine acts as an absolute global rate limit. Even with perfectly partitioned traffic, the worker threads on these nodes will stall if they rely on standard synchronous DNS resolution. Waiting 100 milliseconds to resolve an IP address forces a thread to idle, devastating the aggregate throughput. The solution is to implement custom asynchronous stub resolvers. These run on a dedicated non-blocking event loop. When a worker thread needs an IP address, it registers a callback and immediately moves on to other tasks, only returning to fetch the page once the DNS response is ready. Parallel crawling functions efficiently because the network state is perfectly partitioned. By isolating domains to specific nodes and decoupling DNS lookups, the system scales horizontally without introducing central bottlenecks or violating host rules. Preventing a crawler from downloading the exact same URL twice is solved efficiently in memory using a Bloom filter. But the web is filled with near duplicates, mirrored pages, syndicated articles, and URL aliases that serve identical main text alongside slightly different advertisements or timestamps. These two wireframes show why standard cryptographic hashing fails at detecting these near duplicates. The timestamp on the right page clicks forward by 1 minute. Algorithms like SHA-256 exhibit the avalanche effect. Changing a single character, like a timestamp, produces radically different outputs, masking the fact that the underlying text is identical. To find similarity, the crawler strips the HTML boilerplate and processes the raw text through Cherikar's SymHash algorithm. SymHash tokenizes the words and compresses them into a 64-bit binary fingerprint. Because it is a locality-sensitive hash, similar documents produce similar bit strings. The two web pages with different timestamps now output hashes that differ by only a few bits. In production, documents are classified as near duplicates if their 64-bit SymHash fingerprints differ by a Hamming distance of 3 or less. This creates a massive search problem. Comparing a newly generated 64-bit hash against a distributed database containing billions of existing hashes, looking for a 3-bit variance is computationally impossible using brute force. It would stall the parsing pipeline entirely. To solve this, engineers apply Mancu's block permuted search. The algorithm takes the 64-bit fingerprint and splits it into 4 distinct 16-bit blocks. This relies on the pigeonhole principle. If the maximum allowed difference between two fingerprints is 2 bits, and there are 4 distinct blocks, it is a mathematical certainty that at least one of those 16-bit blocks must remain exactly the same. The database stores 4 separate lookup tables, each permuting a different 16-bit block to the front of the string. When a new page is processed, the system performs a rapid binary search on just the first 16 bits in each table. This specific application of the pigeonhole principle isolates the tiny fraction of hashes that share a 16-bit prefix. It filters out billions of irrelevant records in a single pass, turning an impossible sequential scan into an index lookup that completes in milliseconds. This diagram shows the fully assembled web-scale crawling architecture. A newly discovered URL leaves the Kafka queue, gets prioritized and delayed in the Mercator frontier, resolves its IP through async DNS, downloads via the fetcher, extracts text in the parser, and drops redundant data at the SymHash deduplicator before returning to the queue. This loop's efficiency relies on strict isolation. Network-bound tasks never block the CPU-heavy tasks of parsing and computing. Indexing trillions of documents cannot be achieved by pointing maximum compute power at the internet. It requires throttling execution speeds to respect host limits, partitioning memory state across node clusters, and using statistical hashing to silently drop billions of redundant data points. By combining precise queuing theory with distributed message routing, this architecture safely extracts data from a decentralized, chaotic web and processes it into the highly structured index that powers modern search.